Okay, today I will talk about equilibrium between different phases, uh, between a solid phase and a liquid phase, or let's say between a gaseous phase and a solid phase, or let's say a liquid phase and a gaseous phase. These equilibriums are very important in terms of free energy calculations. We'll be doing a Gibbs free energy calculation for each of the systems, and I was talking about the percentage of questions comes from different chapters. This is maybe the most important chapter of all, and if you just refer to any standard books, they will spend volumes of pages over discussing the different concepts involved in this gaseous phase and what are the equilibrium, how the free energy derivations are coming into picture. But I won't go into that details, otherwise it will be just a demonstration of any standard book. I can just read it out, and that doesn't make sense. So because you were preparing for solving particularly gate questions, so I will very narrow down the key concepts. I'll just briefly explain the key concepts. That will save your time, and that will also help you to build your concepts. Later you can always go on reading the derivations and the exact forms and equations. And after explaining these concepts, I will really go into solving problems, and by solving problems I will explain what are the different concepts that are being used. In the last lecture, you might remember that I talked about between two gaseous phase, a gas is in equilibrium, and when you increase or decrease the pressure, how the free energy changes. It might be between two gases as well, they are in equilibrium. And the real idea is to calculate the free energy of these systems, whether these equations are feasible, and we'll look how these equations are very important in terms of metallurgical processes, and various processes actually exploit this this spontaneity and feasibility of a reaction which will end up in a specific product. So we'll look into that. So let's go to the board again. So today's discussion is about equilibrium between a condensed solid phase and a gas phase, between a condensed solution and a gas phase, and between gas and gas. This I have already covered, so you know how to calculate the free energy calculation. For all this, we are going to calculate the free energy change. This is what the free energy change for the equations, for the reactions. So delta G. So why we are so interested in free energy change? Because free energy change alone tells us whether an equation is whether a reaction is feasible, whether it will move into the forward direction, it will move into the backward direction. It also tells us what are the parameters to drive a reaction into the forward direction. For example, we talk about pressure, temperature. So these equations summarize all these parameters. So that's why free energy calculation is so important. So we'll look how the free energy calculations work here for these systems. So the first thing you are going to you should note that I'm just writing down few key concepts to solve the problems. These are the most essential concepts. Let's see what are they. Fine. The first thing you should always remember that the activity. I will just cover what is activity for the time being. Just remember activity of a pure solid A is equal to 1. Activity of a pure solid substance A, which is activity of a species, let's say I species, is equal to 1. This is the first thing you should always remember. There are derivations. You can just refer to any books. why this activity of a pure solid AI is 1. So for example, MS, which is solid phase, plus hub O2, this is a standard reaction in a lot of the thermodynamic reactions that have. In blast furnaces, for example, we have this the oxidizing reactions. For example, we normally use this for Fe plus half O2. We say it an Fe. It's a standard sort of equations. So I won't mention Fe for, let's say, MS is a solid which reacts with oxygen to form a MO, solid oxide. So if I am going to calculate this activity of this M solid is going to be 1. Okay, so remember this, the activity of a solid phase, of a pure solid phase, is 1. The next thing, please note it down. Next thing, the next thing is, you should always know, I didn't go into the details for the chapter's solution thermodynamics, but mole fraction is very important, So activity is given by mole fraction. Okay, activity is given by mole fraction. So just remember this, according to Raoult's law, Xi is equal to AI. This is the second concept. We'll be needing this particular relationship between activity and mole fraction when the when it's not a pure condensed phase. I just mentioned the pure condensed phase. This Xi is equal to AI is equal to 1. But when this is not a pure condensed phase, the activity is given by the mole fraction. So what is mole fraction? I just recapitulate once. So if there are Na, Nb and Nc moles of material existing in a system, so the mole fraction for Xa is given by Na by sigma Ni, which is basically Na. Basically the expression is Ni by sigma Ni, right? Sigma Ni, which is always given by Na plus Nb plus Nc. So this is the second concept. According to Raoult's law, mole fraction is equal to the activity of the phase in the particular system. Now, the third concept that I'm going to punch in is the concept of partial pressures. What is that? So the partial pressure, you remember the Dalton's law of partial pressures. You can always refer. It's going to be important in some places, so I'm just mentioning. So Xi, or let's say Pi, the partial pressure of a particular component in a system, is given by Xi into P total. So partial pressure of a system is equal to mole fraction multiplied by the total pressure of the system. So this is basically Dalton's law, which you might have studied at your class 2. But this concept is also sometimes useful solving certain kind of problems. Now the fourth concept. In the last lecture, I talked about this equation. Gi is Gi0 plus RT ln Pi, right? This is the free energy. This free energy of a particular phase of a gas, it might be liquid or whatever. Sorry, it should be gas because it's a partial pressure I'm talking about. So the free energy in terms of this standard free energy and its partial pressure in the system. So Gi is given by Gi0 plus RT ln Pi. Similarly, just remember the similarity. If it is not a gas, let's say it's a solid or let's say it's a liquid, Gi is Gi0 plus RT ln AI, where AI is the activity of the component in the system. Okay, and similarly, if you just need to write an equilibrium condition, for example, if you just need to find out what is the free energy changes, so you just replace this for the system. For example, I'll just write for the system to be clear for you. Let's take the system ms plus half O2 is equal to MO solid. This always means it's a solid phase and it's a pure phase. Unless mentioned, just remember that the activity will be 1, but I won't substitute it at the first place. I'll just write what is the free energy. How to write the free energy? This is the final product, right? So the change, if I talk about, so what is the free energy for MOS? This is G, that's GMO, let's say. So the change in free energy at a particular temperature and pressure, which is not a standard one, is what? Is GMO minus GMS minus half GO2. It's a gas, right? So this is the free energy change. Product minus the reactants. The product is MO solid, the reactant is MS solid, and GO2 solid, gas, sorry. So you subtract, you get. Now that to get this, we need to substitute it as an individual equations. How do we do that? We do that as usual. Gi for this GMO 0 plus. Now this one is a solid phase. Let's say if it is not a pure phase, so I will write as RT ln A MO, right? This is the free energy. This is the free energy minus G0 MS plus RT ln A MS, right? Minus, it's visible, right? Minus this one is a gas phase. Remember, this one is in the solid phase. So once there is a solid, this expression is termed in terms of activity. When it is a gas, it will be expressed in terms of partial pressures. So I will write GO2 0 plus, this is a standard state. It's not Z0, it's a standard state. I mentioned what is a standard state. At 1 atmospheric pressure and 25 degrees centigrade, the free energy of a system is termed as its standard free energy. Okay, RT ln P O2. This is the partial pressure at that particular temperature where it is the reaction is being is taking place. So if I summarize this, sorry, I forgot to put a half. So if I summarize this, it's a very important. I'll be solving straightway problems based on this. GTP. So free energy change at a particular pressure and temperature. Normally the pressure is kept constant. We were asked about delta G0. This is, what is delta G0? Delta G0 is the free energy change. I mean Z0 MO minus G0 MS solid minus half G0 O2. Right? This is the delta G0. G0 MS minus G0 M solid minus half G0. Because the stoichiometry fraction is half for O2. That's why there's a half is coming here, right? So we are balancing mole by mole. So this is what happens. Delta G0 is this one. So if you write this, it will look like RT ln activity of solid oxide, divided by activity of M solid multiplied by PO2. Right? This is the very, very important equation. Very important equation for a solid gas equilibriums. So So del GTP is del G0 plus RT ln AMO divided by AMS solid and APO2. It directly comes from this equation. Do the substitution, you get it. So, I just made a mistake. There will be a half over, right? There will be half, because this was half RT ln PO2. There's this term, half RT ln PO2. So half goes over because this is a logarithm. So half this goes over here. So RT ln is the base PO2. Anyway. So for any equilibrium condition, if I want to say that okay, this reaction is in equilibrium, that means again there's no change in the number of moles of the system. The number of moles for solid, oxygen and MO are constant, not changing with time, temperature or pressure. The system is in equilibrium. We say that for that condition, the free energy change to be zero. That is the free energy of this product and the free energy between the difference of free energy between the product and the reactants should be zero. So to establish the condition, delta GTP has to be zero. So if I put it zero, I have a direct correlation ln AMO by AMS solid. It's also solid. PO2 half is minus delta G0 by RT. Normally, no, it's written as AMO solid, AM solid, PO2 half is exponential minus delta G0 by RT. Please understand this one. AMO solid by AMS solid, PO2 half is exponential minus del G0 by RT. So if I substitute, if I say that these are existing in pure solid form, therefore the activity will be 1. So AMO is equal to 1, AM is equal to 1. So it comes to be PO2 minus half is this one, right? So if I want to calculate the partial pressure of a gas, for example here oxygen, in the system for a reaction like this, what would be the partial pressure for equilibrium condition to exist at a temperature T and P? If I say that, so this minus won't be there, right? So if I will just redo it. I'll just redo it, then you will understand why. Okay, one thing, this is also written as sometimes Q, KQ, or K, sometimes written as K. The reactions constant, sometimes referred. The constant, the reaction constant, or the equilibrium constant, we sometimes refer to as equilibrium constant or the reaction constant, whatever it is. It's termed as K. It depends how you define it. So just be a bit more careful here. So let's do it once again. So ln, I'll just erase this one. So this was the equation, right? So RT ln AMO by AM solid, PO2 half is minus delta G0 by RT. R is the universal gas constant, 8.314 is the value. You just check up with the units. T is the temperature in Kelvin. So if I just take this minus 1, I just reverse this one. No, sorry, the RT won't be here. If I just take this minus 1 here, so I just reverse the denominator. So the minus 1 goes from here to here. So here it becomes M solid, PO2 goes to the top, and MO solid comes to the bottom. So So if I substitute AMS and AMO as 1, if the activities are 1, then the expression for partial pressure to maintain equilibrium, the final expression becomes square root of exponential minus delta G0 by RT. The most important equation. For an equilibrium to exist between a solid and this gas and MO solid, the partial pressure of the oxygen gas at that particular temperature and pressure has to be square root of exponential minus del G by RT. Okay, so now I'll just keep on solving problems based on this. Please note this formula very carefully. Okay, fine.